So I know you're incredibly excited about diagonalization. You've probably just gone out and diagonalized a whole bunch of matrices. Totally understandable. We're going to relax a little bit here. Just come back, think a little bit more about basis transformation, and then we'll get into some even more spectacularness of diagonalization. So there's more to come. So this is, yeah, how to change a basis, right? How to change the representation of a vector, right, from one basis to another. So what does that mean? All right, so here's an example. It's just one page. We've got these three vectors here, and I've just pointed them as points, right? They're three vectors, yeah? W1, W2, W3. So that, there's some errors here. Let me fix some things up. So this should be, yes, madness. Okay, so these are actually, this is 2, 2, 2, 2, 2, 2, good. This is why we do these things. So there's a natural, so there's on the left is the natural basis, right? And that's how things, everything we've done is written in terms of the natural basis. Yes, so we sort of have this locked in. But we could use another basis. It's still going to be relative. We're still, you know, we're always going to be anchored in the natural basis. But if we use this different sector system, right, then W1, for example, would be just 2 times A1. It would be just 2 times this vector here. And 0 this way. So its representation would be a 2 and a 0. Yeah, I know what it is. So I put it on the wrong side. So, okay. Right, let's do this. Reference on the one. Okay. Right, I think. So that makes sense. We want to. See, these points are still the same. I mean, this point, right? Still the same points. But we refer to them. We'll say here the basis will represent them in a different way. So W1, for example, here. It's 2, just 2 times the right, I had, and 2 times J had. Just add those together. Good. So how do we get the representation out of W1 in terms of these bases here? How do we do that mathematically? Right, so we could kind of see this one. Not really to scale. This one would be double. W1 would be 2 times A1, and 0 times A2. How do we get that? And how do we do it systematically? And so, of course, we solve an AX equals B problem, right? Not because we're lazy, it's just because so many things really are an AX equals B problem. Right, so our idea will be, let's start with W1. So this is in the natural basis, right? In natural basis, or standard basis. And now we want to write it as some number times A1 and some number times C2. This is the column picture, which you love so much. And so we can write that, we can stack the two vectors, right? This is our new basis. And these are, this would be the coordinates. This is the coordinates of W1 in new basis, in the A1, A2 basis. Right? It says I need this much of A1 and this much of A2, if you like. Okay. So this is some matrix times C1, C2, and for basis transformations, we usually write in, we're going to have M. M will be our matrix there. Okay? Oh, great reason off the right here. So, and I'll put a little subscript for A just to suggest this is a basis, right? So we have W1, this is in the normal basis, W1 in the A basis. Same point, but they you know, they're both 2 by 1 vectors. So if we have this transfer, right, it's very simple. We just stack these two vectors together to make a matrix, that actually takes us from, this is a bit weird, it takes us from the representation in this new basis back to the standard basis. So we need this. That happens. Right, so we need, right, so we need to, so this, so the inverse takes us from the, I know this is a little, this will feel a little funny, from the natural to new basis. This is an easy thing to mess up, but so just sort of think through this logic here. So we find the inverse of this matrix, 1, 1 minus 1, 1, which we've done for our for diagonalization. We've done this before, so that's the same inverse. Compute it, and we get 2, 0, which is what I was saying before. So this is 2 times A1 and then 0 of A2. So this is W1 in the A1, A2 basis. You have to say which basis you're using. And you can do the others. If you might want to test this out, you can get them to be 2. You'll see the 2, 1 and 1, 1. And to change back, we invert it, right? So let me maybe, right. So we've got this way of doing things, and to change back, we'd go like this, right? Okay, good. So, just an example of how we talk about things. So in the natural basis, 1, 0, 0, 1, W1 is represented as 2, 2. In this 1, 1 minus 1, 1 basis, which isn't, they're not univectors, doesn't matter, then W1 is represented as 2, 0. These are the same, right? They specify the same point slash vector in space. Right, even though this is just sitting here as a 2, 0, it's 2, 0, where the 2 means 2 times that A1 vector and 0 times A2 vector. So, big deal, right? And here it is, right? So as I've said, right? The vector never changes, but our representation does. Yeah? And if we think about diagonalization again, right, I've talked through this, but here we can see it again. This s to the minus 1 is really acting as this new matrix, this basis transformation matrix inverse that we just talked about for a general problem. S is then the matrix, the basis transformation that takes us from the eigenvector basis and brings us back. This one takes us from the natural basis to the eigenvector basis. And this is the, I've called it a change vector, right? This is the one that does the actual work, right? Does the stretching and shrinking or whatever it is. Right, this changes basis only, and I'll put in here from normal to eigenvector. Right, so we're multiplying a vector x, will change its representation, and then once we've done the work here, we can change the basis back, and this is from eigenvector basis to normal. All right, so it's easy to get this kind of back to front, but work through this and you should be able to see how things make sense. All right, basis transformation, big deal.